Have you ever dreamed of visiting the past? Perhaps you wish to witness historical events firsthand, or maybe you long to glimpse the distant future. The idea of time travel captivates the human imagination. For centuries, it has been a staple of stories and dreams. But is it merely a fantasy, confined to the pages of fiction? Or could the laws of physics, in their deepest and most mysterious workings, actually permit such extraordinary journeys? This question challenges our everyday understanding of time as a relentless, forward-flowing river. Science fiction often portrays time machines as common devices. Characters step into a booth or activate a gadget. They then find themselves in another era. The reality of time travel research is far more complex. It is grounded in the intricate theories of physics. Scientists explore these ideas with caution and rigor. The allure of controlling time is immense. Such an ability would reshape our existence. It would alter our understanding of cause and effect. It would redefine what it means to be human in this vast cosmos. Our comprehension of the universe is constantly expanding. What seems impossible today might become understandable tomorrow. The history of science is filled with such transformations. Theories that once seemed outlandish are now accepted facts. So what exactly is a wormhole? Imagine a tunnel. This tunnel does not go through a mountain or under the sea. Instead, it is a theoretical passage through spacetime itself. Spacetime is the very fabric of our universe. A wormhole could connect two very distant points in this fabric. It could link our galaxy to another, millions of light years away. Some theories even suggest wormholes could connect to entirely different universes. These are mind-bending ideas, born from complex mathematics. The term wormhole offers a helpful analogy. Think of an apple. A worm wants to get from one side of the apple to the other. It could crawl all the way around the apple's surface. This is a long journey. Or the worm could burrow directly through the apple. This creates a much shorter path. A wormhole is like that burrow. It is a shortcut. It bypasses the vast distances of normal space. This simple image helps us grasp a very complex idea. Wormholes are not just random guesses or flights of fancy. They emerge from the equations of Albert Einstein's theory of general relativity. To understand wormholes, we must first understand Einstein's view of the universe. His theory of general relativity, published in 1915, revolutionized physics. Before Einstein, space was seen as a fixed, empty stage. Time was thought to flow uniformly for everyone. Einstein showed this was not true. He proposed that space and time are linked. They form a single, dynamic entity. This entity is called spacetime. It is a four-dimensional fabric that makes up our universe. This was a radical departure from previous ideas. Einstein also explained how gravity works. He said that mass and energy warp or curve space-time. Imagine placing a heavy bowling ball on a stretched rubber sheet or a trampoline. The bowling ball creates a dip in the sheet. Now, if you roll a marble nearby, it will curve towards the bowling ball. It is not because the bowling ball pulls the marble directly. It is because the marble is following the curve in the sheet. In the same way, planets orbit stars because they are following curves in space-time. These curves are created by the star's mass. This warping of space-time can be very extreme. Near very massive objects, space-time can be bent dramatically. Black holes are an example of this. A black hole is a region where gravity is so strong that nothing, not even light, can escape. Let's try to visualize how a wormhole could work as a shortcut. Imagine space-time as a large sheet of paper. Mark 2 points on opposite ends of the paper. These points represent two distant locations in the universe. To travel between them normally, you would have to cross the entire sheet. This could be a very long journey. Now fold the paper. Bring the two marked points very close to each other. Then imagine punching a hole through the paper. This hole directly connects the 2 points. This hole is like a wormhole. A theoretical wormhole has specific parts. It has 2 mouths. These are the entrances or exits of the tunnel. It also has a throat. This is the narrowest part of the tunnel connecting the 2 mouths. To use a wormhole, a spacecraft would enter one mouth. It would then travel through the throat. Finally, it would exit from the other mouth. This journey could be much shorter than traveling through normal space. The distance through the wormhole's throat might be relatively small, even if its mouths are light years apart in the wider universe. The universe is incredibly vast. Our nearest star, Proxima Centauri, is over 4 light years away. This means light itself takes 4 years to travel that distance. Section 5, the Wormhole Cookbook: Ingredients for a Space-Time Shortcut. Creating or finding a wormhole is not a simple matter. The laws of physics impose very strict conditions. First, immense gravitational forces are needed. These forces would be required to bend space-time so dramatically. The kind of curvature needed for a wormhole is extreme. It is far beyond what ordinary matter like stars or planets can produce. Even black holes with their intense gravity do not automatically form stable, traversable wormholes according to current theories. This is a significant challenge for the idea of naturally occurring wormholes. To keep a wormhole open and stable, scientists believe something extraordinary is needed. This ingredient is called exotic matter. Exotic matter is not like anything we know. It would have very unusual properties. Specifically, it would need to have negative mass or negative energy density. Think of normal matter, which has positive mass and pulls things together through gravity. Exotic matter would do the opposite. It would effectively have anti-gravity properties. It would push space-time apart. This is a crucial theoretical requirement. Why is exotic matter necessary? According to general relativity, a wormhole made of normal matter would be incredibly unstable. Its own gravity would cause it to collapse instantly. Section 6. Echoes in the Cosmos. The hunt for wormhole evidence. It's crucial to remember that wormholes remain firmly in the realm of theory. They are elegant mathematical solutions to Einstein's equations. But do these mathematical structures correspond to anything real in our universe? So far, we have no direct observational evidence that wormholes exist. Scientists have not pointed a telescope at the sky and seen a wormhole mouth. The search for them is ongoing, but it is incredibly challenging. They are, for now, ghosts in the mathematical machine of general relativity. Detecting wormholes, if they exist, would be a monumental task. They might be incredibly small, perhaps at subatomic scales, or they could be located in very distant parts of the universe. Their effects on their surroundings might also be very subtle. Finding a wormhole could be like searching for a specific, unique grain of sand on all the beaches of the world. The universe is vast and complex. Pinpointing such an exotic object requires clever ideas and powerful instruments. We are still figuring out what to even look for. Section 7. Time Machines and Paradoxes. The Wormhole Conundrum. The connection between wormholes and time travel is one of their most captivating aspects. How could a tunnel through space also become a tunnel through time? The answer lies in Einstein's theories of relativity. Specifically, it involves the phenomenon of time dilation. Time dilation means that time can pass at different rates for different observers. This can happen if one observer is moving at very high speeds, or if one observer is in a much stronger gravitational field than another. These effects are real and have been experimentally verified. Imagine we have a traversable wormhole with two mouths, A and B. Initially they are close together and clocks at both mouths are synchronized. Now suppose we take mouth B on a journey. We accelerate it to near the speed of light, then bring it back. Due to time dilation, time will have passed slower for mouth B. So if mouth A's clock reads the year 2050, mouth B's clock might read 2040. If you enter mouth B in 2040 and exit mouth A, you would emerge in 2050. But if you enter mouth A in 2050 and exit mouth B, you would emerge in 2040, 10 years in the past. This possibility of traveling to the past raises many logical puzzles. These are known as time travel paradoxes. Section 8. The Great Debate: Science, Speculation, and Wormholes. What is the current scientific consensus on wormholes and time travel? Most physicists view traversable wormholes as highly speculative. The need for exotic matter is a major hurdle. Exotic matter with negative mass energy density has never been observed. Without it, wormholes would collapse too quickly. This makes them seem like a mathematical possibility rather than a physical one. Despite skepticism, the topic remains a subject of active research. Some physicists, like Kip Thorne, have explored wormholes in detail. They investigate conditions under which wormholes might exist. This exploration pushes the boundaries of our knowledge. However, many believe wormholes will remain mathematical curiosities. They might be interesting solutions to Einstein's equations, but they may not represent objects that can form in our universe. The hurdles, such as exotic matter and potential paradoxes, seem immense. Some argue that unknown laws of physics might forbid traversable wormholes or time travel. Section 9. Future Frontiers: Seeking Tunnels and Unraveling Mysteries. The quest to understand wormholes continues. Researchers are engaged in theoretical work. Some aim to construct wormholes without exotic matter, or with minimal amounts. Others explore alternative gravity theories. These theories predict different wormhole properties. The goal is to see if cosmic tunnels are possible. The challenge is immense, but the drive to explore is strong. Future technology could play a crucial role. We are entering an era of powerful telescopes. Instruments like the James Webb Space Telescope offer unprecedented views. Gravitational wave observatories like LIGO and Virgo open new windows. Future upgrades might detect wormhole signatures. This could be a specific lensing pattern or wave signal. Many questions remain unresolved. Are wormholes possible or just mathematical artifacts? Can exotic matter for stable wormholes exist? If time travel through wormholes is possible, how are paradoxes resolved? These are not easy questions. They lie at the edge of our understanding of physics. Answering them may require breakthroughs, perhaps a unified theory of quantum gravity. Thanks for watching. If you like this kind of exploratory video content, please like, comment, share, and subscribe.